Hi everybody, this is a video going over the differences between two types of PCA filters in Homer2 and kind of actually explaining it's the same filter essentially. Let me go ahead and start a slideshow here and let me just check one thing. Alright. Okay, so in Homer2 you have the option of running a PCA filter. The options you'll see in particular this enPCAfilter and then this hmrMotionCorrectPCA filter. We'll start with the enPCA filter, and this is the input-output. So the input is going to be the ESD struct, the D, and the T inc. The SD struct is actually readily available. It's the coordinates of your data, where the sources and detectors are located. And this SD mes list act stands for all the channels that are active in that, and they all should be active unless you've manually tweaked them or run a motion artifact detection algorithm, which we'll get to in this. The D is your data that should already be readily available, and the T inc is basically very similar to that mes list act. It's a vector of just saying what time points are included in the data and which are not. So the mes list act is showing what channels are active. The T inc is showing which time points are active. And both of those are indicative of whether or not you've kind of marked or flagged data as inappropriate. So the only input value that you will be responsible for is this NSV, and this is the number of components that you want to remove from your data. It comes in two forms, and it's actually in the same box. So if you do a decimal form, it's going to say we're going to remove as much principal components as are needed to remove variance up to that percentage. If you do an integer, it's going to say we want to remove this many principal components. So you can play with it one way or the other. And then your output, the only output that's really probably most used is going to be this DN, which is just your corrected data. The SVs and the NSV are there, but I don't know anybody who's actually accessed those other than to cite them. I'm sure they could be useful though, so don't take my word on that. If you remove them by fraction, I've kind of given you an example. This was just a very basic data set, nothing too noisy, especially within the data itself. But this is running the enPCA filter. And if you notice, I've used an NSV value of 0.1 to 0.5, and all of them were identical. There was actually nothing removed. What that indicates to me is that I would imagine that the data is fairly clean, that there's not much going on with that. Once you get to 0.6, though, you'll notice not much has changed about the data itself other than the scale. The scale has dropped down a little bit, which means that it's become less, the variance has shrunk a little bit. 0.7, again, same thing happens. 0.8, all of a sudden the values look a little bit more compressed and within range, and then it gets more and more and more that way. Once you get to a value that, if you look at this, the range of the actual experiment is 0.005, so it's quite small. Once you remove too much, it's not really giving you anything useful at that point. You've probably removed any significance from anything in the data. So you want to be, not too aggressive in this. And if you are having to find yourself being too aggressive, perhaps that your data is not the most high quality. Aside from removing by fraction, though, you can also remove by integer. So rather than saying 0.1 or 0.2 or 0.3, we can say 1 or 2 or 3. And this is instead of saying I'm going to remove so many principal components to remove this percentage of data, I'm just going to say let's just remove this many principal components. And this is what one looks like, which is very not so different from our first value here. And in fact, it looks more like 0.6 at that point. So that's our first principal component removed. At 2, we're a little bit more compressed. At 3, at 4, and then once you get to 40, which was what I could max out at, and I believe the max value depends on your data set itself and how many components exist. But once I got to 40, I really don't have anything going on. It's just completely flat data. Again, find. I don't know if I can instruct anyone with any form of confidence as to what values are the best, but I'm sure there are some individuals out there who can help, and I'm also sure it has to do with the data set that you're dealing with. So on that note, how much is too much? I don't think there is a right answer to this, but just make note, this is applying to the entire data set. So, during the experiment may be very different than before or after the experiment. You could have, some overlap because of one or the other fading into each other because of that. Maybe that's a concern for how you apply this. But just be cautious when applying PCA and don't go too aggressive with it. When applying hmrMotionCorrectPCA, this is going to be the input and the output. They're actually identical. There's no change here. Again, the only variable that you're going to deal with is this NSV. And the greater the value you put, the more flat your data will become. The output will be your filtered data. But there's one big catch with this. With the MotionCorrectPCA, you have to have preemptively already identified motion, which means, let me go to my MATLAB here. When pulling this up, I need to convert my data to optical density, and then I need to call this motion artifact to flag my motion. And what that means is anything, depending on what my threshold values for a motion artifact are, whether I'm using standard deviation or amplitude threshold. And I have a video on what those mean that I would suggest clicking on if you need help with that. Depending on what you set as those, it's going to flag or mark time sections as motion. It's not going to do anything with them though. This is where this comes in. So it's going to say everything that's flagged as motion, perform PCA up to that point. If I was using the enPCA filter, I wouldn't need to flag any motion artifacts because it's applying to the whole data set. So that's where the big difference between these two comes into play. And again, you figure out what range you're comfortable with, whether it's a fraction or a decimal, or whether it's an integer value in that NSV input. And this is what it's doing. So this mimics the last slide I had, or a few slides back that I had, where I actually changed the NSV value from 0.1. I just jumped ahead to 0.5 so you could see an obvious change, 0.9. And once you get to 0.99, you'll notice the area within this flagged section is very flat compared to everything outside. Nothing has occurred to anything outside the section. I've only treated everything inside the section. That's when you deal with fraction, with the decimal aspect of it. You can also, again, do integer value, and I do 1, 4, 8, and then up to 30. In this case, I actually wasn't even able to go to 40, and I'm assuming that's because I have a shorter time period, and therefore probably fewer components involved in it. But it's doing the same exact processing, just on a different range of data. And so in this case, you're not looking at the whole data set. I've had to zoom in on one particular location, and in fact, I had to use a different data set that had motion in it. That would be flagged. I could have probably been more aggressive with my flagging of motion artifacts, but this was a little easier to do. And it's only doing this PCA filter within that range. It leaves everything else alone. The similarity is you're using the same input variable. That input variable is asking how much variance do I want to remove. The more you remove, the flatter your data gets, and the more significant you're removing. The less you do, the noisier data is, and the more likely you have some randomness that probably isn't right in there. The differences are, again, the enPCA filter is acting on the entire data set. You're not specifying what region you want to apply it to. I think that can be quite good in one sense because it's uniform across and you're not kind of playing favorites, if you will. But it also can be quite bad because you're actually kind of like using components that may not have to do with different regions or something like that. You're manipulating everything where you may not really need to. So there's an advantage and a disadvantage to that. Whereas the motion correct, same thing. You're not being uniform across the whole data set. You're playing favorites, but at the same time, you're not manipulating data that you don't necessarily need to. So, take it as you will. I'm again not in the position or the capacity to tell anyone which one is most correct. But at least you should be able to identify what they're doing, and so you can make an educated decision on that. Anyway, I hope that was helpful. And if you guys have any more requests or questions, just send me a comment or an email, and I'll be happy to help.